This, this experiment is asking for floating ground because all of the equipments are connected through the common ground that we have in here. Everything has a 3 prongs, and this is the ground. So your scope and your function generator has a common ground, and if you look at the circuit diagram, a common ground will give you a 0 output. So we need to make it to be a floating ground by connecting, let's say, the scope like this, and connect this thing to the output. Cut this part. It requires a capacitor to be connected to your function generator. So this is the capacitor, function generator positive. The negative part of the function generator goes to the part of the resistor right in here. See, this is the other side of the function generator. Now, this side, the two are connected, and your channel 1 goes this side of the capacitor, which is, this is channel 1. The positive side goes to the positive, and the negative side of this thing goes to the negative, which is a common ground. So this is the common ground for everything in here, so that's my ground right there. Actually, the other side is the ground right here. That's the ground. It has been marked. Now, and resistor is connected. So everything is connected. Now we got to do channel 2. Channel 2 goes this side of this and the common ground, which is right there. Well, that's okay. Now, again, remember that since we have a floating ground, this wire, which is coming from our function generator, which has a negative, is connected to the positive of this one, so they are not actually the same point. Otherwise, they're going to be these. Otherwise, you will have basically shorted the resistor, and you would not be able to see anything. If you do not have a common ground, what you will be seeing in the channel B is a flat line, because you have grounded, you have shorted the resistor. Okay, that's the reason for common ground.
Go ahead. Right now what we're looking at is a voltage waveform. So you might think it looks like a current waveform, but they have a similar structure to it. But the voltage divided by the resistance, in this case using 1,000 ohms, will give you the waveform of the current.
Right. The top one is the input voltage. The bottom one is the voltage across the resistor, which is the same as the current across the resistor in terms of format, but you got to divide that by a value of the resistance, which is here is the 1K. So they are the same thing. We are interested in voltage of the capacitor versus its current. Next, we're going to shift these two, move them, and find the phase shifts. Okay, then you can expand the two signals and combine them in order to find the phase shift between the voltage and the current. Remember that for a capacitor, we have the equation I equal to C dV over dt, and channel 1 was the voltage, channel 2 represented the current. And when you find the phase shift using the cursor, it shows at 27.200 microseconds. When you convert that thing, since we have 10 kilohertz in here, you get 97.92, which is supposed to be around 90, which is good enough.
Here's the kilohertz.
Yeah. Okay. For the part 3, you will change the waveform to a triangular waveform and make it 1000 hertz, not from 10 kilohertz that you had before. You make it 1000. It should be 10 volts peak to peak, so we're going to change that thing a little bit, close enough to 10. That should work. All right, and take a picture of this part. Okay, now the next part is we're going to turn this thing to a square waveform, and again, this is the current waveform that we are seeing in the bottom. What we are interested in this part is to find a time which is about 63.2% of the total charge. So this is the drop time that we are interested in to find in the next stage. All right. So I want to show you how to do it. For the last part of this experiment, we need to find the 0.632% of the peak value of the waveform, which is actually here is a voltage for the output. So in order to do that, we have expanded the output and got rid of the input voltage, which was a derivative of a square waveform. And we want to find out 0.632% of that. Before we do that, we're going to find out what's the maximum of this, which is supposed to be about 10 volts, but it may not be. It may be changing when we do all these measurements. So this is about, for this one, it's about 9.84. It could be 9.92, whatever it is for you. So that's the value. You multiply these things by 0.632%, and then bring down the cursor for that. Let's say it's about 6 point something in here, 6.4, 6.21. About here, 6.2421. So the point that is hitting the is the distance from the y-axis or to this point is what we wanted. That's the time. That's the delta time we want. So I'm going to be changing the cursor to the time and move this thing to the y-axis, and this is exactly hitting it right there. And you see the delta is 3.60 for this measurement. Okay, that concludes this experiment.